Hey class, welcome to our 2.5 notes on acceleration and one-dimensional kinematics. Now this is going to be broken into two parts, so we're going to do part one acceleration and then we'll expand upon it doing kinematics. And so luckily for us, we kind of already have an understanding of what acceleration is. It's a term used, you might have heard accelerate or decelerate, which usually just means to slow down. But we know this term acceleration because we've graphed velocity versus time. Let's go ahead and get ourselves a definition for acceleration. So acceleration is the change in velocity over time. Ooh. Got a little carried away there. Change in velocity over time. And if I were to write that in equation form, I would get A for acceleration, which is equal to delta V, which is change in velocity, divided by time. Now, another way you're going to see this written out is the final velocity, that's what that F is, minus the initial velocity, or V naught, divided by time. So, as I look at this, I now have four variables involved in an equation, which is the most we've had so far, and we're going to continue to expand upon this in kinematics. But what do I measure acceleration in? Well, to do a little unit analysis here, we're going to take velocity, which is meters per second. We're going to divide that by the time, which is in seconds, which would give me meters per second, or meters per second squared. This is my unit for acceleration. So now that I have the unit, I can move on and I can, get a little practice here. But let's make sure we define these variables. We have our A is acceleration. VF is my final velocity, so where I end up. V naught is my initial velocity, so where I start. And then lastly, that T is time. So let's get some practice using our new equation, and we can apply it in a couple different ways, find different variables. So our first practice here, a car is at a red light. When it turns green, it takes 8 seconds to accelerate up to 15 meters per second. Find the car's average acceleration. Now, it's important that we use our guess method. So if we have forgotten what the guess method is, we write out our givens, then we figure out what our unknown is, or what I'm looking for. Then we write down our blank equation. Then we substitute in our numbers to the equation, and then we solve the actual equation. And when we're working this on a free response problem, each of those is worth one of the 5 points for the free response problem. So make sure you're taking your time in every step. This is also where physics students start to separate out. If you are willing to walk through the method, you're going to have a really easy time here. If you're unwilling or think that you can just do it all in your head or all in your calculator, you're going to struggle for a couple reasons. Number one, I won't know what your work is. I can't help you, and I can't read your mind. So I need you to show your work. And secondly, the getting in the process of learning how to identify problems and move forward with them is a skill needed in this class that isn't just going to apply to this equation. There's going to be sometimes you got to do one equation and then gear it to a second one, and it's really hard to do those in your head. So walk through the process, and I guarantee you'll have a much easier time than if you just do it in your head. So let's start with our given. So what do I know? Well, I know 8 seconds here. That's my time. So T is equal to 8 seconds. I'm going to accelerate up to 15 meters per second. So that's going to give me my final velocity. And then you might be a little confused because, well, I need something else here, because if I'm going to do acceleration, which is what we're aiming towards here, which is VF minus V naught over T, I'm missing my initial velocity. Well, sometimes we have to use context clues within our problem. And here, the context clue is that the car is at a red light. And if you've ever been in a car, you know that a red light means stopped. So that would tell me that my initial velocity is 0 meters per second. Another term you might hear is this term at rest. And It means that I'm at 0, whether I start at rest or I go to a rest. Now, we've done the givens. Great job. Now I got to identify my unknown, which is find the car's average acceleration. And my car's average acceleration is A. So A is my unknown. So we did that. Great job. We did our equation already. We already wrote it out. So A is equal to the final velocity minus the initial velocity divided by time. So I did my equation step. And now we're just substituting and solving here. So I'm going to plug in my values. A is equal to 15 minus 0 divided by 8. I'm going to solve that top portion first. So I'm going to get 15 divided by 8. And then I'm going to get it into my decimal form here, which is going to be 1.88 meters per second squared. And then you're going to box in your answer to let everyone know how smart you are. So that's our steps. There we go. We did substitute and solve. So there's 5 points right there. And notice, if I was talking through this with you and you got the wrong answer, I'd be able to see exactly where you went wrong. Maybe you miscalculated. Maybe you did 0 minus 15, you got a negative. Maybe you flipped t and you multiplied it. Maybe you did something, but I can see your work, and that's what the crucial part is here. So we've got 2 more practices here. So let's go ahead and take a look at them. So a child is going on a sled at 7 meters per second. If he is slowing at a rate of negative 2.5 meters per second squared, how long will it take him to come to a stop? All right, so once again, we're going to go through our guess method. What are my givens? Well, the sled is going 7 meters per second, so that's how fast it is currently going. It's slowing at a rate of negative 2.5 meters per second squared. This squared would tell me that I have the acceleration of negative 2.5 meters per second squared. But again, I'm out of numbers. Well, how long will it take him to come to a stop would imply that I'm looking for the final velocity to be 0 meters per second. All right, well then what's my unknown here? How long will it take? I'm looking for t. There we go. And then I need my equation. So that's the next step. And I have acceleration, velocities, and time. So it's going to be A is equal to VF minus V naught over T. And then I can substitute in my values. So this is a good time to maybe pause the video and work through it yourself and maybe try. But if you're still having trouble, you're welcome to continue working it with me. Negative 2.5 is equal to 0 minus 7 over T. I'm going to solve that top part. 2.5 is equal to negative 7 over T. I'm going to multiply both sides by T here. So that'll cancel those, and I'll get negative 2.5 T is equal to negative 7. And then I will divide by negative 2.5 to get me T is equal to 2.8 seconds. Well, there you go. So notice we used our acceleration equation. We just solved for a different value, which on your worksheet here in a second, you're going to have to rearrange everything into different values, which is just asking you to do this. So let's do our last problem. This one we're going to rearrange first and then solve, substitute and solve. So let's go ahead and look at number 3. A ball is rolling down a hill with a velocity of 2 meters per second. If it had an average acceleration of 0.6 meters per second squared, what will the ball's velocity be after 6 seconds? So again, we're going to go through guess. So what are my knowns? It starts with a velocity of 2 meters per second. That's my initial velocity, 2 meters per second. Has an average acceleration of 0.06. So there's my A, 0.6 meters per second squared. What will the ball's velocity be after 6 seconds? There's my T. And I have all my values. Well, my unknown here, what will the ball's velocity be? So that's going to be my final velocity is what I'm looking for. And then I got to go to my equation. So acceleration over T. And this time, instead of substituting my numbers in first, I'm going to rearrange my equation and then substitute and solve. So I'm going to start by multiplying both sides by T. to get that t out of the denominator because fractions are not fun to deal with. And then I'm going to add v naught to both sides. And that's going to get me at plus v naught is equal to v final, which now I can substitute in. So I'm going to substitute in my values. I'm going to go to the right here and say at, which is 0.6 times 6 plus my initial velocity of 2, which gives me 3.6 plus 2, which will then be 5.6 meters per second is how quickly my ball is going to be going at the end of the hill. Now, I'm going to continue on in these notes, but what I want you to do here is pause the video, go do part 1 of the worksheet, which would be 1 through 5. And when you see 1D kinematics, you're going to pause there. But if you are through, when you're done, come back and we'll continue on in this. So I'm going to move on in the notes here to 1D kinematics. Now, kinematics is a big scary word. It really is. It sounds very sciencey, but all it is it relates everything we've learned together into how things move. So we get what are known as the kinematic variables. Which are everything that we've learned so far, which is our initial velocity, the final velocity, Vf, acceleration, A, T for time, and then delta x for displacement. So now I have everything in one place. And with this, kinematics gives us 3 equations that allows us to better manipulate what's going on. So that gives us our kinematic equations. Now, depending on who you ask, there's either 3 or 4 kinematic equations. We only use 3 of them. So our kinematic equations go as such. Our first one is one that we've seen before. It is our acceleration equation rearranged to get velocity final. So you've seen this, but you might notice it's missing something. It's missing displacement. So I need another equation that relates those. We have our displacement equation for that, which you would notice this beginning part is just our velocity equation rearranged to equal displacement. But because these objects are accelerating, we have to tag on a bit here on the end to get us if case our object is accelerating. Our last one is our time independent equation, which just means that, we don't need time. And it's 2 times acceleration times the displacement. And together these equations allow us to understand anything that's moving at a constant acceleration. And because of that, it makes doing the math really easy. Now, this is a moment where a lot of physics students either continue on or kind of start to fall behind, and that is because of organization. So as we work through these problems, I want you to see how I organize the problem, and I'm going to talk you through it. That way, we have a better understanding of what's going on. So let's look at this first practice problem here. It's exactly like our one before, but we're going to kind of shift a little bit up in what needs to go on. So the car is at the red light. When the light turns green, it takes 8 seconds for the car to accelerate to 15 meters per second. Find the car's displacement during that time. All right, let's figure it out. So we know on a kinematics equation, I'm just going to write out all 5 because sometimes I end up needing all 5 of them or 4 out of the 5. So we just, anytime we see this, we're going to write them out. V naught, Vf, A, T, delta, x. So when I do this, I'm then going to go to my problem. I'm going to find my knowns. So I see 8 seconds. So 8 seconds is going to go here. We accelerate up to 15. We know that. And then I also know that V initial is 0 because I was at a red light. Okay. Now I would ask myself, okay, so what kinematics equation am I going to need to use? So let's go ahead and come back up here. And let's go ahead and grab these guys. And we're going to drag these guys down to help us out. So we're going to duplicate them. We're going to drag them down. And we want to try and figure out which equation I want to use. So let's see. Okay, what equations have V initial? Well, if I go through, this one's got V initial, this has, so they all have V initial. All right, V final. Okay, that's got V final. Ooh, second equation does not have V final. And this has V final. All right, what about T? Well, this has T. Oh, the other one doesn't have T. Ooh, we're running into a bit of a problem here. I need my acceleration. And sometimes this will happen, where you need a fourth one in order to figure everything else out. And lucky for us, we found acceleration on our last problem. It was 1.88 meters per second squared. Oh, look at that. I can now pick any equation that I want. And we are going to pick our first or our second one here, just because it's already in delta x equals form. So we're going to write out our equation blankly. So delta x is equal to v naught t plus 1/2 a t squared. Then we're going to substitute. So we have 0 times 8 plus 1/2 times 1.88 times 8 squared. And because I have this, important to know that that squared only applies to the t. So then I start plugging values in, and I find that my acceleration, my displacement is 60.16 meters. Very nice. Let's do two more. We're going to kind of roll a little bit here. And again, if you want to try them on your own, try it on your own, and then check the answers. So here on number 2, a sprinter going at a velocity of 10.8 meters per second and begins to slow to a stop. If they slow with an average rate of negative 3.2, how far did they travel? Kinematics problem. Going to immediately write out everything. And start identifying my variables. So going at a velocity of 10.8. So that's going to be my initial velocity. It's going to slow to a stop, so that would mean my final velocity is going to be 0 meters per second, and I have an average rate of 3.2 meters per second squared. There are my knowns. How far did they travel? Well, that's going to be delta x. So if I go back and look at my 3 equations again, which one does not have time? Well, that's going to be my third equation here, which is my time-independent equation. So let's go ahead and use that equation, which is vf squared equals v naught squared plus 2a delta x. There's my equation, step 3 of guess right there. Let's go to our 4th step, substitute in. 0 squared is equal to 10.8 squared plus 2 times negative 3.2 times delta x. Well, then I'm going to go ahead and solve some of this out real quick. So 0 squared is 0. 10.8 squared is 116.64 minus 6.4 delta x. And from this point, it's just algebra. So I'm going to add 6.4 delta x to both sides because I don't like negatives. And I'm going to divide both sides by 6.4. And that's going to get me a delta x value of 18.23 meters. I hope you're getting the hang of this because it's really a practice in organization, a practice in identifying what information I have finding the tool I need to figure out that information, and then solving through using the proper tools. If I try to use the wrong kinematic equation, well, it's not going to go as well because I need a certain kinematic equation to solve a problem. So let's look at one more, and then I will release you to go ahead and work on the end of worksheet 1.5. So a train is traveling at 22 meters per second. It slows down to 16 meters per second as it approaches a turn. If this took 50 seconds to slow down, what was the train's average velocity? Well, let's start as we have every one. Oh, V initial. Got a little too excited there. V initial, VF, A, T, delta, X. Well, the train is traveling at 22 meters per second. It slows down to 16 meters per second. And it took 50 seconds to do that. You can see I'm moving a lot quicker now. What was the train's average acceleration? So I'm looking for A. So I'd go back up to my equation, and you can look at what you've got written down. And I'm going to use equation number 1. VF equals V naught plus AT. And then I'm going to plug in my values. 16 is equal to 22 plus 50A. I'm going to subtract 22 on both sides, get me negative 6 is equal to 50A. Divide both sides by 50, and that's going to get me an acceleration value of negative 0.12 meters per second squared. All right, I hope you got some good work here. I hope you have a good understanding. If you have questions, come ask me. And good luck on finishing worksheet 1.5.